everyone. Today we are going to kick off Chapter 7. Chapter 7 is all about powers and exponents, and this first lesson is kind of a standalone lesson, but it focuses on something called power functions. So we're going to be talking about graphing these functions that are written in this form, and if you need to pause the video to get the definition written down, that's fine. But it's functions of the form y equals x to the power of n, and just in case that's too small for you to see, this is what a power function always looks like. It's just x to some power, okay? And we're going to talk about what effect that power might have on the shape of the graph. Now, we've been working with one of these power functions pretty extensively throughout the last chapter. If I put a 2 in here and I have y equals x squared, you should be very familiar with that graph. You should be very familiar with what that type of graph looks like. It's a parabola, right? So what we want to look at today is what happens when I use powers other than 2. What happens if I do x to the third, x to the fourth, x to the fifth, and so on. And I kind of gave this part away here by setting up this table for you, but what you're going to find is that all of the even power functions have something in common and all of the odd power functions have something in common. Now, I put here k is positive, k is negative. I don't know if that was a typo on my part. There's not really a k value here. This would be more like when it's just x to the power of n, and then this would be like when there's a negative sign in front of that x to the n. So we're going to talk about what effect does that negative sign have on the function or on the graph of the function. But first let's take a look at what happens anytime I have an even power. And so I should have Desmos pulled up here somewhere. There we go. Oh, sorry for the delay here. But what we're going to do is we're going to graph y equals x squared. Okay, that's our parabola that we're very familiar with, right? We all know what that one's going to look like. Now I'm going to do some other even powers. I'm going to do x to the fourth, x to the sixth, x to the eighth, and maybe x to the 10th. And we could probably even go, we could do like x to the 26th, let's say. Okay? And so what I want you to notice is that all of these functions have the same general kind of U-shaped graph. What's happening is that bottom part is flattening out a little bit. Now this one, this x to the 26th, that's pretty extreme. It looks like it's almost flat and almost vertical. It's not really. It does still have a curve to it. It just starts to flatten out the bigger that exponent is. So a couple of things I want to point out to you. So first of all of these even power functions do have that U shape to them. And we're going to write this down in your notes in just a minute. Again, as the power gets bigger, you tend to see this bottom part flattening out a little more. Okay, and again, it's not truly horizontal, but it just gets closer and closer to 0 there. I do want you to notice that all of these graphs contain this point here. They all sit right at 0, 0, because no matter what the power is, 0 to the power of whatever is always going to be 0. And that's going to be something that all of these power functions have in common. All of the power functions contain the point 0, 0. These ones also all contain the point 1, 1, because 1 to the power of anything is 1. And that's another one that is going to be true on every power function. 1 to the power of anything is 1. On the even power functions, we're also going to have -1, 1, because -1 raised to any even power is going to come out positive. So there's these 3 points here that all of those even power functions share in common. Okay, so let's go back to our notes here, and let's sketch ourselves a picture here that even power functions are always going to have a U shape to them. You're going to be tempted to call them parabolas, and I probably won't correct you, but I should just point out that technically only the x squared function is called a parabola. The rest of these we just say have kind of a U shape to them. Okay. A couple of things you should know about this function is that it does include the point 0, 0. They also all include the point 1, 1. And these two would be the two that I think are most important for you to know, because these are actually going to show up on the odd power functions as well. If you wanted to, you could show that this one also includes the point -1, 1, no matter what the power is. I think you're also going to run into questions about domain and range. domain for power function, so if you look back up at the kind of the generic function up here, there's never any restrictions on what I'm allowed to put in here for x. No matter what the power is, I can put anything in there that I want for x. So my domain here is always going to be all real numbers. This thing goes forever left to right. So domain is all reals. With the even power functions, my range, notice the graph always stays on the top half of the graph. So my range is going to be all real numbers greater than or equal to 0, everything above 0. Okay. The other thing I should point out is this graph has reflection symmetry over the y-axis. So with parabolas, we talked about it having an axis of symmetry. If these are all centered right at 0, 0, that line of symmetry is always going to be the y-axis. So let's just make a note here, and I should have left a little more space at the bottom, but this has reflection symmetry over the y-axis. And the reason that's important, the reason that symmetry is important, is if I pick any point on the graph, so if I pick this point right here, and let's just call it x comma y, I know that I can go straight across to the other side and find the point negative x comma y. That symmetry tells me that I'm always going to have like twins. I'm always going to have pairs of points that correspond, one with a positive x and one with a negative x. But every point will have kind of a partner that lies on the other side of that line. Okay. Okay, let's go back and look now at what some of the odd powers look like. So let me just get rid of these guys. So let's look at x to the power of 3, x to the power of 5. Maybe I don't need to do as many this time. We'll do those 3. And you will notice that these functions all have kind of this sort of squiggly shape. They all start down here in the third quadrant. They come up, they sort of zigzag through the middle, and then they keep going. If you zoom in here, you will see that, again, these share some points in common. They also contain 0, 0, because, again, 0 to any power is 0. They also contain the point 1, 1. So these 2 points are common for all your power functions. And then this one, because odd powers keep numbers negative. So if I take a negative number and raise to an odd power, it stays negative. This one contains the point negative 1, negative 1. Because when you raise a negative to an odd power, you get a negative back, okay? So going back to our notes here, if we kind of wanted to sketch this, let's see, our odd power functions. And again, there's not really a name for this. I always just call it like a squiggle-shaped graph, but it kind of looks like this, okay? And a couple of notable properties. Again, this contains the point 0, 0. It also contains the point 1, 1. Okay, if you wanted to, you could show that it contains the point negative 1, negative 1. For my domain on this one, again, like I said, all power functions are going to have a domain of all real numbers because the graph goes forever left to right. There's no restrictions on what I can put in here for x. On this one, my range is also all real numbers because you're not restricted. You've got positives up here and you've got negatives down here. So this one goes up and down, which gives you a domain and range of all reals. This one does not have reflection symmetry, but it has what's called rotational symmetry about the origin or around the origin. And what that means is if I put my pen down on this center of this graph here and I take it and I spin this thing 180 degrees, this part of the graph would end up down here. So it can spin and land back on top of itself. That's what it means to have rotational symmetry. Now, at first glance, these graphs might look like they're doing 2 totally different things. But I want to point out that if you look at just the first quadrant, these graphs actually look really similar to each other, right? This curve here and this curve here really look very similar. The difference is how they behave with negative x values. So if you look at the left side of the graph, this is where the difference comes in. With an even power, if you've got an even number here, any negative number that you plug in is going to be turned positive because you'll have an even number of negatives, right? And so we've already talked about how when you square a negative, it always comes out positive. That's going to be true with any even power. So the negative numbers turn positive. You've got coordinates that are negative, comma, positive. With odd powers, those negative numbers stay negative. So it's really like I'm taking this half of the graph here and just kind of turning it downward in the opposite direction when I do the odd power function. Okay. For that reason, if I have a point up here that's x comma y, that rotational symmetry means that I'm also going to have a point down here that is negative x, negative y. That's what that rotational symmetry does. This is saying that if I put in a positive value, I get a positive value out. If I put in that same value but negative, I'm going to get the same answer, but the answer will be negative. Okay, that's what the rotational symmetry means. So, and again, just to kind of drive my point home here, let's look at just x cubed, compared to an even power function like x to the, I'm going to do x to the fourth just because we work with x squared all the time. And so if you look at the, right side of this graph, the purple and the red look very similar. The purple one grows a little faster just because 4 is larger than 3. Okay, but these have the same general shape over here on the right. If you look at the left side of the graph, the purple one heads upward while the red one heads downward. That's because the odd power turns negative, or keeps negative numbers negative. The even power turns negative numbers positive. That's going to be a really important relationship to understand. Now I want you to think for a second and maybe even pause the video and contemplate this for a minute. What do you think would happen if I threw a negative sign in front of this x cubed? And maybe think about what happened with parabolas when we threw negatives in front of them. Okay, I'm going to turn off the x to the, I'm going to turn off x cubed for a second. Let's just look at x to the fourth. If I throw a negative sign in front of here, what I'm going to end up with is a vertical flip. Okay, my graph is going to flip over. It's going to point the other direction because we're taking all those positive values that we were getting a second ago and turning them all negative. Okay, if I were working, so here's positive, here's negative. Okay, that's the effect of that negative value. If I were working with an odd power function like x cubed and I throw a negative in front of it, the same thing is going to happen, but this half of the graph on the right is going to end up down here. And this graph that's already on the bottom half is going to flip up to the top. So watch what happens when I do this. There's my negative x cubed. There's positive, negative, positive, negative. Okay, and so it is really doing a vertical flip. I know sometimes it seems like it's, I don't know, rotating or flipping a different way. Whoops, didn't need to do 2 negatives there. But the negative is going to have the same effect whether you're working with an even or an odd power function. What the negative is going to do in both cases is flip your graph upside down. So with the even power functions, it's just going to make an upside down U shape. On this one, it's going to make it so that this basically goes in the other quadrants. It's going to go this way. Okay. These things are still true. The symmetry pieces still hold true. The domain is still all real numbers, so I can still say my domain is all reals and my domain is all reals. The only thing that changes now is the range, and actually it only changes for this one. In this one, my range, because now my parabola points downwards. Oh, and see, I did it there too. I shouldn't have called that a parabola. My range is everything less than or equal to 0. On this one, my range would actually still stay the same as well. Okay, so you can fill that into your table in whatever way works best for you. Do want to point out that these graphs do still contain the point 0, 0. All of these graphs contain 0, 0. They won't contain 1, 1 or anymore just because of that negative. They would actually contain the point -1, -1. Or sorry, 1, -1 is what I meant to say. That would be down here in this lower right quadrant. Okay, so let's talk some math with these. Let's do some examples here. So this first example says the point -2, 256 is on the graph of a power function. And as soon as I see power function, I'm thinking y equals x to some power. So the question is this power function even or odd? This would be a great time again to pause the video and think about that, and then come back and I'll explain. We know this is an even power function because I took a negative number and put it in and it came out with a positive result. So because I went from a negative value to a positive value, that tells me I must be working with an even power function. If it were an odd power function, my negative value would have given me a negative y value as well. So now to write an equation. This is what our equation is going to look like. Really, we just need to figure out what number goes here. So the question we're asking ourselves is -2 to what power makes 256? And we know it has to be even. Okay, we know it has to be an even power. Your best bet at this point is some guess and check. There are some mathematical ways to solve for this. We haven't really talked about that this year. So what I would do is I would just take -2 in parentheses, because anytime you do a power with a negative, it's got to be in parentheses, and I would start raising it to some even powers. Now, I'm fairly confident I know what -2 to the second power is, and it's not 256. So I'm going to start with a power of 4. Okay, oh, that's 16. All right, so that won't work. So let's do a power of 6. Nope, still not it. How about a power of 8? Notice I'm only picking evens because we already determined it would have to be an even power. There we go. Okay, so it's -2 to the 8th power. So that means my equation is just y equals x to the 8th power. Okay, so figuring out the power for right now, our best bet is just to do some guess and check. Name 3 other points on this graph. We have talked about 2 points that are on every power function. So the very first thing I would do is list those 2 points. Those 2 points are, another good time to pause and see if you remember, but 0, 0, and 1, 1 are automatically on any power function. Now I just need one other point. And really, this is the equation I'm using. So let me just put anything in there for x that I want. So let's say I'm going to plug in a 3 here. So I'm going to go 3 to the 8th power, and I'm going to get a y value back out. So 3 to the power of 8 gives me 65, 61. And I just picked that 3 out of thin air. I mean, we can pick anything. We're just making up our own points. So I would go 3, comma, 6561. Okay. The other thing we could have done and saved us a little bit of work here is we could have used that whole idea of symmetry. So if the point -2, 256 is on the graph, then we know the point +2, comma, 256 would also be on the graph. So we could have named that one as well. Okay, let's see if we can just sketch these guys on a coordinate plane. Do we have, and I don't need exact points here, although I will again remind you that the point 0, 0 and 1, 1 are going to show up on every one of these, well, except for this one that's turned upside down. Okay, so x cubed, that's going to have kind of that squiggle shape, and so I'll do x cubed here in red, and so that's going to come up kind of like this. It's going to zigzag through the center and look like that. I could probably smooth that out some. I know it's going to contain that point there, but so that would be your x cubed. Really, I just want you to understand the shape of these graphs. Okay, x to the 4th. I'm just digging for another color here. X to the 4th, that's an even power function. We'll do this one in blue. That's going to be more parabola shaped, and it is going to grow faster than x cubed, so I'm keeping it on the inside of that red line. Really, it should probably actually swoop down like this, a little flatter. If you didn't know that, I mean, right now, the shape of the graph is the most important, but you'll start to learn kind of the characteristics of these graphs as you graph them. So the bigger the power, the flatter it is down here at the bottom. So I wanted it to be a little bit flatter than what I'm seeing here. Oh, and then I should fill in the other side of this graph, which is going to look something like this. Okay, so overall we have this blue line that represents y equals x to the 4th. Not my best drawing ever. And then last one, y equals x to the 8th power. That is so it's going to be an even power, so it's going to be U-shaped. but it is also going to be upside down because of that negative sign. So I'm just going to do a U-shaped graph that's kind of pointing upside down. Still digging for colors here. So I'll use purple for this one. That's going to contain this point and this point. And so it's going to be very flat and come down like this. And of course I picked a color that's not really working. Way to go, me. Go. So key things for you to know is, first of all, when is it U-shaped versus when is it like squiggle shaped? Okay, very technical terminology here. You should know that every single one of these graphs is going to contain the point 0, 0. It will also contain, 1, 1 or negative 1, 1, depending on which type of function it is, whether it's a positive or a negative. And you should understand that the bigger your exponent goes, the flatter it's going to be here in this region around the origin. Okay? And again, you should have been able to do all of that without graphing them in a calculator. That's really it on power functions. That's all the important stuff I have to tell you about power functions. So you're going to head off and do some homework for me now. This is kind of a standalone lesson. It doesn't really lead to other content in this chapter, but we will circle back to these ideas of exponents and, even powers versus odd powers. That's going to be a pretty big topic moving forward. Okay, that's it for me today. Have a great day.